In this video, we're going to look at verifying the solution of a recurrence relation. So it says consider the non-homogeneous linear recurrence relation given here. So it's non-homogeneous because of the plus 2 to the power of n being added onto our subscript terms, and it's linear because none of our subscript terms are being multiplied together or raised to a power. Now we need to show that this here is a solution of this recurrence relation. Now when we talk about a solution of a recurrence relation, we're talking about the closed form. Okay, so this here should be the closed form of an, and the reason it's potentially the closed form is because an is written entirely in terms of n and there's no subscript terms. Now we need to check it's the closed form, and to do that we are going to substitute this into my recurrence relation and check that both sides come out as equal, like you do for any equation. So if we look inside my recurrence relation at the subscript terms, we have a of n. Well, we can replace the a of n with what a of n is equal to here, negative 2 to the power of n plus 1. But then we also have the a of n subtract 1. So what are we going to replace that with? Well, we have to go to my potential solution, and we're going to replace the n with an n minus 1. So we'd have a n minus 1 is equal to, and I'd replace all the n's on the right-hand side with an n minus 1. So this n here is going to get replaced with an n minus 1. So we'd have negative 2 to the power of n minus 1, and then it's plus 1. Like that, because of this plus 1 here. Now let's just simplify this. So we get a of n minus 1 is equal to negative 2 and then power of, and it would just be the power of n, because negative 1 plus 1 gives me 0. So now we have all the information we need to substitute into my recurrence relation. So let's start doing it. So an is going to be the negative 2 to the power of n plus 1. So negative 2 to the power of n plus 1. And then that's going to be equal to our 3 here, multiplying our a n subtract 1. So multiplying this here, so I'm going to write multiplied by, and then we've got negative 2 to the power of n. And then let's make sure we write out our non-homogeneous part, so the plus 2 to the power of n, like that. Now I have to show that the left-hand side is definitely going to be equal to the right-hand side. So what I'm going to do is go to my left-hand side and my right-hand side and make sure they're written in the exact same format. So on my right-hand side, I can see that my powers of 2 have a power of n in each case, whereas on my left-hand side, it's a power of n plus 1. I don't like that. I want to change that. So I think it's probably going to be easier to change the power of n plus 1 into the power of n, because usually it's often a bit easier to go to the smaller power, but also the n plus 1 only appears once, whereas the n appears twice. Okay, so if I want to change a power of n plus 1 into a power of n, let's consider how we're going to do that over here. So I've got negative 2 and then power of n plus 1. And just to be clear, this negative here is representing negative 1 times 2 to the power of n plus 1, like this. Okay, this isn't the number negative 2 raised to the power of n plus 1, because that would then be written in brackets like this. Okay, order of operations says we do indices first, and then we do the subtraction or multiplication, however you want to see that negative sign in front. Okay, so we can write it like this over here on the right. Now I want the power of 2 to reduce by 1. So to make that happen, I'm going to divide by the same base, which is 2, and I just have to decide my power. Okay, if I want n plus 1 to go down to n, I need it to decrease by 1. When we divide, we subtract the powers, so I need a power of 1 here, because n plus 1 subtract 1 gives me n. So that's going to become 2 to the power of n. The problem is if I divide by 2, I've now changed the value of my term, and I don't want that to happen. I need to keep the value the same. So how am I going to cancel out dividing by 2? Well, you're going to multiply by 2. Okay, so negative 1 times 2 would give me negative 2. Okay, and then we're going to put our multiplication symbol in. So the left-hand side can be written as negative 2 times 2 to the power of n. And then I'm going to write in my right-hand side like this. Now the left-hand side is written with 2 to the power of n only appearing once. I want the right-hand side to be of that same format. Okay, so let's consider how we're going to simplify. Well, we do have like terms on the right-hand side. We have a 2 to the power of n multiplying in there and 2 to the power of n in this term. Again, there's no other n present, so they're like terms. So we should be able to combine them together by addition and subtraction. And we've got addition here. So what I'm going to do is I'm just going to rewrite things slightly on that side. Okay, we're going to take this negative sign, which just represents a negative 1 multiplying the 2 to the power of n. I'm going to multiply it by the 3 to get negative 3 times 2 to the power of n. And then this 2 to the power of n, I'm going to write it in the same format, because we got negative 3 lots of 2 to the power of n. well, how many lots of 2 to the power of n do I have here? Well, I have one lot of 2 to the power of n like that. So on my right-hand side, I have negative 3 lots of 2 to the power of n plus 1 lot. So that's going to give me negative 2 lots of 2 to the power of n. So I'd have my left-hand side, and then my right-hand side would become negative 2 times 2 to the power of n. And as you can see, my left-hand side and my right-hand side are going to be equal for all values of n. So I can say, therefore, left-hand side is equal to right-hand side. So the an is equal to the negative 2 to the power of n plus 1 is a solution of the recurrence relation. So just make sure that you get that concluding statement in there because it's a show that question. So let's have a look at another question. Okay, so let's have a look at our question here. So we've got another recurrence relation, and this time there are 3 subscript terms, and the difference between the largest subscript n and the smallest one, n subtract 2, is 2. So therefore, this is a second order recurrence relation. However, it is a homogeneous one because there's nothing being added or subtracted on to our subscript terms. Now we need to verify that the following solution satisfies this recurrence relation. So we're going to substitute it in and check the left-hand side is equal to the right-hand side. So let's go through our subscript terms. We have un, so I can replace that with 3n plus 5. Now we got un subtract 1, so I'm going to need an expression for that. So un subtract 1 essentially means I'm replacing n with n subtract 1. So I'm going to go to the right-hand side and replace this n here with an n subtract 1. So I would get 3 lots of n subtract 1 plus 5. And I'm just going to expand and simplify that. So I would get 3n subtract 3 plus 5 when I expand the brackets. And that would become, if I write it on my next line, un subtract 1 is equal to, and it would be 3n, negative 3 plus 5 would be plus 2, like that. So I've got an expression for un subtract 1. It's going to be 3n plus 2. What I now need is an expression for un subtract 2. So I'm going to write un subtract 2 here. And I need to go to my possible solution, or the solution that I'm verifying, and I'm going to replace the n with an n subtract 2. So replace this n here, we would get 3 lots of n subtract 2, and it would be plus 5. Now let's expand. So if I expand, I would get 3n subtract 6 plus 5. And if I simplify, I get un subtract 2 plus 3n, negative 6 plus 5 is negative 1. Okay, so I've got the 3 bits of information that I'm going to have to substitute in to my recurrence relation. So let's begin the substitution. Okay, the un is going to be replaced with the 3n plus 5. So I'm going to write that here. And then on my right-hand side, I've got the 2, and that's multiplied by un subtract 1, which is going to be the 3n plus 2. So I'm going to put that in brackets. And then we've got subtract, and then we've got the un subtract 2, which is the 3n subtract 1. So I'm also going to put that in brackets because it's multiple terms. Now let's expand and simplify my right-hand side. So 2 lots of 3n is 6n, 2 lots of 2 is 4. And then the negative subtracting the brackets, so we're going to multiply by negative 1. So we get negative 3n, and then we get positive 1. Now let's collect like terms on my right-hand side to fully simplify, because my left-hand side is already fully simplified, so that's fine. And what we're going to get is 6n subtract 3n is 3n, and then 4 plus 1 is 5. So I can say, therefore, the left-hand side is equal to the right-hand side. So the solution that I was considering, so the un is equal to 3n plus 5, is a solution of the recurrence relation.